and they travel in the blood as methylated estrogens. And then if the body needs it for something, they take the methyl group back off again, and it's an estrogen again. But this oxidation happens all the time. And so far so good because the catechol-estrogens aren't reactive. But if they get further oxidized to the catechol-estrogen quinones, those are reactive. They're highly reactive.
With DNA.
With DNA, or also with proteins, or with peptides. Like for example, they react with glutathione, which is a big scavenger in the body. And that's a nice protective mechanism. But they can react with DNA in very specific ways that can start the process leading to cancer.
So it's like a carcinogen, right? I mean, just
yes,
like
it's
an
a carcinogen.
X-ray or...
It's an endogenous carcinogen then, yes.
Hey friends, welcome back. Today's show is brought to you by our pals over at HelloNed.com, the makers of a broad-spectrum phytocannabinoid blend derived from hemp that's biodynamically grown, which means that they're not using pesticides and herbicides that are harmful for your health. And another unique factor that really separates HelloNed from all the other hemp-derived phytocannabinoid blends that are out there. A lot of that stuff is made in China. They're using caustic agents like benzene and toluene to pull out the bioactives that can end up in the finished product and can inadvertently harm your health. And that's why I love this company. And most importantly, I like the transparency. So again, there's a ton of hemp products out there to choose from. Virtually none of them are providing their certificate of analysis and third-party testing on their website, showing each lot is free of things like Roundup and benzene and harsh chemicals. And so you can find all this information right on their website over at HelloNed.com. And you can use the URL HelloNed.com/HIH to save 15% off some of their amazing products that I personally use and recommend. You know, how would you use something like a broad spectrum phytocannabinoid? Well, very simply, to improve your sleep, to take the mental edge off with all the uncertainty in the world, the economy, the election, there's a lot of unknowns. And so instead of turning to things that are unsustainable and have, poor habitual formations like alcohol or opioids or other things, I like to have my clients leverage things like a broad spectrum phytocannabinoid blend from hemp because it doesn't cause some of those deleterious issues. It can improve your sleep and take that edge off. So you can support your body's endocannabinoid system tone by going over to HelloNed.com/HIH. Again, one more time, that URL is HelloNed.com/HIH. All right, so today's show is a really fun discussion with someone who I've been following for a long time. Her name is Eleanor Rogan. She's a PhD at University of Nebraska. So I traveled to Dr. Jamie Seaman's conference in January of this year and was able to sneak out a little bit and catch up with Eleanor, and it's an amazing discussion. Now, I just want to preface this, that we talk about a lot of biochemistry. We talk about really estrogen metabolism and how estrogen catechol-quinones, and we'll define what that is, how they can literally, basically, for lack of a better word, grab DNA, the guanine residues, and cause mutations that lead to cancer, specifically breast cancer. And that's why I would love for you to share this video with anyone in your life, both men and women, because estrogen quinones can be created in the prostate and drive prostate cancer. So anyone who's had a familiar history or knows of someone who's had breast cancer or prostate cancer or a scare, they need to watch this video because they are going to learn so much about estrogen metabolism. And again, someone who is really involved in the research. She's an amazing person. We really dove into the weeds. So if you're new to this channel, links will be below to the show notes, and we have timestamps. You're welcome to, and some of the references that we talk about in Eleanor's work. So I'm not going to keep rambling. Let's cut to it with Eleanor Rogan, and I hope you enjoy this conversation. Now, how'd you get so involved in estrogen catechol-quinones and metabolism?
Well, so I was part of a joint research group with another scientist named Ercole Cavalieri, and when we started out, we were working on the polycyclic aromatic hydrocarbons, which are combustion products, and
are those made by combustion of cooking foods and things like that, like charboiled meats? Is that
they're anything that you burn organically. They come from the combustion of wood or coal or natural gas or gasoline or anything like that. If it's got, and food, cooking food too also.
Okay.
Like in charbroiled steaks, there was a lot of controversy about charbroiled steaks.
Yeah.
Okay. So we studied those mechanisms, and then eventually we understood the mechanisms that were involved in initiating cancer. Out of them, we switched over to estrogens, which behave differently, but there's a lot of similarities. And what it took us 25 years to do with the PAH, we then got to the same place with the estrogens in about 5 years because we knew what to look for. And so we got interested in them because we had always thought that they were an endogenous initiator of cancer. But when we started, we didn't have the tools. The tools just weren't available to work on the estrogens. They're just for chemical reasons. They were a lot harder to work on.
Was this in the 90s or early 2000s when you started?
This was the 90s. We started the estrogen. First paper that was published was in 1992.
Wow.
And so then the estrogen work proceeded a lot faster, and we got to the point a little bit after 2000 that we could begin working in human tissue, and human, actually we moved then into working with human urine and blood, and which is a lot easier.
Yeah.
And so
fascinating. I think that there's not too many people, Eleanor, that understand this idea. Is it estrogens? Is it the E2?
Well, there's Estrone is E1 and Estradiol is E2.
Okay.
And they interconvert back and forth all the time. So we study both of them because they just go back and forth metabolically. And so they can, they normally, those are the estrogens. They normally, when they travel they normally have an extra, I'm not sure how technical to get here.
Let's get technical. That's fine.
Okay,
Yeah.
an extra hydroxyl group out of them. They're catechol-estrogens then, and then those can be methylated, and they travel in the blood as methylated estrogens. And then if the body needs it for something, they take the methyl group back off again, and it's an estrogen again. So, but this oxidation happens. It happens all the time. And so far so good because the catechol-estrogens aren't reactive. But if they get further oxidized to the catechol-estrogen quinones, those are reactive. They're highly reactive.
With DNA.
With DNA, or also with proteins, or with peptides. Like for example, they react with glutathione, which is a big scavenger in the body. So, and that's a nice protective mechanism. But they can react with DNA in very specific ways that can start the process leading to cancer.
So it's like a carcinogen, right? I mean, just
yes,
like
it's
an
a carcinogen.
X-ray or...
It's an endogenous carcinogen then. Yes, exactly.
Gosh, so much to unpack there. But just to go back to this hydroxylation step, is that through the cytochrome P450
It's
enzymes?
through the cytochrome P450s.
Okay.
There's like hundreds of cytochrome P450s.
Right.
Cytochrome P450, the 1As generally put that extra hydroxyl group on to the 2 position in the molecule of either estrone or estradiol. Doesn't matter. The dangerous one is if it goes on at the 4 position, which happens to cytochrome P450 1B1, and that's pretty specific to 1B1, and so then that goes on to make a quinone from that, and that's highly reactive with DNA. Much more reactive than the quinone from if you start out with the 2 catechol-estrogen.
So it's the 4 catechol-estrogen
Right.
that really preferentially converts to the carcinogenic
Right.
catechol-estrogen
Right.
quinone that's reactive.
Yes. Right.
Now, interesting, I mean, I want to keep diving into this whole, but the PAHs and some of these environmental inducers of these cytochrome P450 enzymes can upregulate. So
They can upregulate, absolutely.
So we have genetic variability in the expression of these enzymes, right? Like some people can just be born, say, with a fast 1B1. So they could be making more of these estrogens, but also, to my knowledge, and please correct everyone if I'm wrong, we can take things in our environment that can cause this P450 system in certain, for example, I can't remember, maybe caffeine upregulates one, I think grapefruit inhibits some, so there's all these different natural compounds, right? So along those lines, I guess kind of two-part question, maybe we can tackle them one by one, I guess. The genetic variability of individuals with a fast cytochrome P451B1, is that more common? Is that linked with breast cancer? I think I remember seeing a few.
It has been linked with breast cancer. I think one of the problems here is it may be pretty difficult to do a study where you can show a link with one enzyme like that. You may need to look at a bigger pathway. I'll give you an example of a study we did and got results beyond what we ever imagined we would get. We looked at women with and without ovarian cancer, and we found what we expected, which was that women with ovarian cancer have higher levels of estrogen DNA adducts than women who don't have ovarian cancer. That didn't surprise us. We were happy to see it, but it wasn't a surprise. At the same time, we looked at the polymorphic variations in two enzymes. Yeah. One of them was cytochrome P451B1, and as it happened, what we looked at was a variant that made it more active. And we also looked at catechol-o-methyltransferase, which is a good protective enzyme, and the one we looked at, the polymorphism we looked at, made it less active. So what we found in these women was that if they had the less active catechol-o-methyltransferase, the two copies of the less active catechol-o-methyltransferase, plus either one or two copies of the more active cytochrome P451B1, they were 3 times more likely to have ovarian cancer. But for the women who had 2 copies of the more active P451B1 and 2 copies of the less active catechol-o-methyltransferase, they were 6 times more likely to have ovarian cancer. That's a huge effect.
Wow.
And so that supports this whole concept that it's the formation of these adducts that is starting the process that begins to put a cell down the road to being a cancer cell.
And where were you measuring these? Is this just in whole blood?
Okay, so if you have a genetic polymorphism, you have it in every cell in your body.
Gotcha.
So it doesn't matter where you measure it from.
Right.
And we were measuring the adducts in urine because that's easy.
Okay.
And we can also measure them in blood, and you get the same results.
Fascinating. So if I heard you correctly, it's kind of a double whammy. If you're making these quinones faster and you have an inability to metabolize them through the COMT pathway, which I think a lot of our listeners are pretty familiar with some of these different...
Right. It's the step before the quinones, it's the catechols, because normally you make the catechol-estrogen, and if your COMT is working properly, you put a methyl group on it, and that's kind of the end of the story. It can't form a quinone then. So if that's working right, then you have lower levels of quinones, so you get lower levels of adducts. On the other hand, if your catechol-o-methyltransferase isn't working so well, and you make the catechol-estrogen, it can go on and be a quinone and react with DNA.
Okay. What I'll do is overlay some images of some of the papers right now, because I think people seeing this, I used to sell dietary supplements to doctors, and one of the products that we would talk to doctors about is glucoraphanin and sulforaphane, because it does help, and methylation support for people that have a familiar risk, or if they know their genes. And sometimes some doctors would want to push the glutathione side of the equation as well. So it's pretty interesting that there's a lot of nutritional interventions here, should you know your genes.
Absolutely.
There's mixed feelings about getting one's genes tested, right? because people feel like it's doomsday. Oh, I'm predisposed to this. I have all these problems. But I think, as Jeff Bland, who is how I found your work back in 2007, has really talked about, understanding your potential as well. Like where can you really thrive and highlight?
Exactly.
Are you a fan of people testing their genes? Like looking at these different?
Yeah, yes, I'm a fan of doing that. I have to admit I haven't done that, but
Personally?
Personally, no, I have not.
Yeah.
But yeah, I think that would. I think it can be very useful. I guess I would say I'm a fan of doing that if you do have some kind of a healthcare professional that you could work with in order to take advantage of this. So you would, who could really understand those results.
Yeah.
I have a feeling that if you just try to do this and then
figure it out
by yourself, you're probably going to go down a lot of rabbit holes. Yeah.
Yeah, you're like, what does cytochrome P453A4 do? Or I have a,
And whether things are really going to be important or not be important, because there's an awful lot of redundancy in the system.
Sure. Well, from a mechanistic, evolutionary teleologic perspective, do these quinones, catechol-o-methyltransferase quinones, do they serve any purpose? I mean,
I don't know of any purpose. But I'm not exactly, I'm not willing to say there is one. It's just I don't know what it would be. Yeah. Certainly, no, I don't know.
It's hard to...
Yeah. The other molecule that goes through this there's only one other molecule that goes through this kind of metabolism, and that's dopamine.
Dopamine, quinones, and...
Yeah. So, now, but the dopamine, and it all depends on the pH. And if you're at pH, typical pH 7, you won't form the quinones. It goes another way.
For just dopamine or estrogen?
No, just for dopamine.
Is that just in the central nervous system tissue or systemic or?
Actually, dopamine is actually everywhere, but it's concentrated in the brain, in the dopaminergic neurons.
Fascinating. Now, is that linked with, say, Parkinson's, the dopamine quinones in that?
We would like to study that. And again, it's one of these situations where, even to be specific about it, when Michael J. Fox formed his foundation and they're putting out all these things about we want innovative ideas. Well, no, they didn't want this innovative idea, that's for sure. I mean, they had zero interest in pursuing this. And I keep... Long ago, NIH grants had enough money in them that you could kind of bootleg a little something, but that is really not true anymore. And so I keep hoping to have enough money that we could pick this up again in the lab.
That would be amazing.
Yeah.
Just for curiosity's sake, how much money would you need to study something? Is it a couple $100,000 or 50 grand? Like,
I think we could, with very specifically for dopamine and Parkinson's, we could probably know whether we were on the track of something useful with a couple $100,000, probably, because we need to synthesize it. We know how to synthesize the adducts. We've done that, and we need to resynthesize them and then see. Actually, we have some ideas to do this in cell culture first to see if we could make everything work in there, and if that then go into animals if it was available, or maybe into humans.
Wow.
Yeah.
I mean, it seems like there's pretty wealthy people out there that may have a family or a friend or someone that have Parkinson's that would be like, hey, let's look at this, because that could be very interesting. And a lot of the drugs that are being administered, this is super off target, but maybe we can just go here, Adderall and Ritalin and things like that, these dopaminergic type drugs, you wonder if taking those sort of compounds would increase the formation of the dopamine quinones. I recall someone talking about that. I haven't looked at that research. Have you?
No, I've not looked at that.
Yeah. Anyway, it's super fascinating. So this quinone formation is specific to dopamine and estrogen. Do the dopamine quinones also damage DNA? Mm-hmm.
Yes, they make the analogous DNA adducts. Mm-hmm. We've published that.
And they're called depurinating adducts because
Okay, these adducts form only on the purine basis. You know, you have two purines, the A's and the G's, and two pyrimidines, the C's and the T's, or U's, or T's in DNA. And they only form on the purines. And then when they form, because of the position and the bond that's made, the bond to the deoxyribose breaks. And that process of its breaking is depurination. And so we named them depurinating adducts. It might not be the best name, but we don't know what else to call them.
I think it's good.
They fall out because of depurination. Yeah.
So if people can visualize the DNA double helix, basically what these adducts are doing is like taking a step off the ladder.
Right. You have a little gap there. You have a little space with no message. So that when the DNA replicates, any base can go in there, in this little gap. And sometimes it'll be the right base and nothing happens. Sometimes it'll be the wrong base, but it doesn't affect whatever happens after, whatever that DNA is for, it doesn't affect it. And then sometimes you get a change that really starts to lead a cell down in an important place, probably in an oncogene or a tumor suppressor gene.
Mm-hmm. So if you were to start removing these purines from, say, P53, like you mentioned, tumor suppressor gene, over 5-10 years, right, then that gene may not function, and should it need to be upregulated to prevent some sort of neoplasm, it doesn't have the information. It's like, if someone were to maybe look at an encyclopedia and the pages were starting to be ripped out.
Well, there's a very good example of this, which is not from the estrogens, but from aflatoxin. And aflatoxin makes an adduct, overwhelmingly, it makes one adduct with guanine, and that adduct depurinates. And if you have liver cancer, if you get they've shown that liver cancer from places like, South China, which I gather it can be very hot and humid, and you have a lot of aflatoxin, and they've shown there's a lot of aflatoxin there. And a lot of people who consume rice with aflatoxin on it, their liver tumors have a very specific mutation there in their P53 gene. But if you look at liver tumors from, let's say, Japan, where there are really strict rules and you don't have aflatoxin there, their liver tumors don't have that mutation in the P53 gene. Or if you look in people from Scandinavia, where they don't have much problem with aflatoxin either, you don't see that mutation. So the best example I know of showing that an apurinic site from a carcinogen DNA adduct that depurinated ended up with this oncogenic mutation.
Is P53 sensitive to these sort of depurinating adducts for whatever reason, or is that just one gene that they...
I think it just happens to be one gene where this has been found. I think it's true of other genes, and we just haven't been able to do the research to figure out what they might be.
Yeah, gosh. Any companies commercially available? I know there's a few in the Pacific Northwest that are doing urinary testing of estrogen metabolites, where you can sort of triangulate and figure out. The so-called Dutch test looks at this. Mark Newman, he's been trying to create an assay. I don't know where it's at this point in time to look at this. Is there any tests that a lot of people look at the 2:16 ratios of estrogen metabolites, but not too many people or too many labs or even doctors are focused on the 4 hydroxy.
There's been an interest, actually, now you got to say it's for 10 years now, to have this, the kind of looking at estrogen DNA adducts available, particularly among the functional medicine group. I know that they would like to be able to look at this. And the problem is, we do this analysis all the time in our lab. The problem is in taking what we do in the lab and putting it into a commercial setting so you could do it at some reasonable cost in this commercial setting. Because well, the way to go with this is with tandem mass spectrometry. That's the way you can analyze these compounds. And we then take the mass spec results and by hand we analyze them. That's the sticking point in this, because nobody can do that on a commercial basis. You have to,
scalable.
and so, however, there are some people looking at it and trying to make this work, and I really hope they'll be successful, because I know this would fill a really big gap and would enable a lot of people to get better data about cancer risk.
Absolutely. Yeah, I mean, it seems like a lot of people kind of focus on, there's a few different genes. I mean, this seems like a key pathway. Like, would you, I mean, maybe speaking off the cuff and some of the research, is there a way to quantify, maybe loosely triangulate, roughly how much estrogen-related cancer could be caused to this mechanism of these depurinating adducts from estrogen metabolites? There's a lot of folks on the BRCA1 and these other genes.
Right. Well, my personal opinion is it's fundamental to a variety of kinds of cancer. It's the fundamental mechanism. I mean, certainly if you think of breast cancer and
Ovarian, you mentioned.
Ovarian cancer, and I mean, I'm sure that's what's going on there. It's also, I'm sure it's also true in prostate cancer. Interestingly enough, another scientist back in the mid-90s was working on prostate cancer and had a strain of rats that's susceptible. And before we met and began working together, he had already published that, in his opinion, that prostate cancer was initiated by estrogens and then promoted by testosterone. And I think that's still true today. I mean, I think what he got to with a very different kinds of study, a simple study, which was when he just implanted his rats with testosterone, about 40% of them got prostate tumors. If he gave them a good dose of estradiol before that, and then he implanted them, 100% of them. So that's what led him to this idea of the initiator being estrogens, and out of DNA damage. He couldn't get at that time to DNA damage, but that was, we subsequently showed that the prostate can and does do this metabolism. And we've since published a couple of papers about how men with prostate cancer have high levels of estrogen DNA adducts. The problem with that kind of a study, I have to say, is that if all you can do is compare people with and without cancer, you can't then say, well, they have cancer because they had adducts. Maybe they have adducts because they had cancer. That's the problem with that. Now, I think we've got some evidence that gets around that, in that when we study women in breast cancer, we also have a pretty well-defined group of women at high risk, according to the Gale model score. And that's a pretty good, it's not perfect, but it's pretty good. And those women have high levels of estrogen DNA adducts long before they have any detectable tumors. So that's one kind of evidence. And then I think also the evidence that we got in this study of ovarian cancer and the polymorphisms, that also supports this whole notion. This model.
Now, are you in these women? I know it's not commercially available, but was this a urine measurement of their adducts?
They've mostly been urine, but we've also done it in serum.
Okay, so it's found. They're found throughout the body.
Yeah.
Now, does the body make antibodies against these adducts? Because I know if you have loose DNA, is it scleroderma or lupus, where you create an autoimmune sort of reaction? Have you looked at that? Okay.
No.
So I
wouldn't.
thought the immune system freaks out like, whoa, DNA, what are you doing floating around here? You're not supposed to be here. I didn't know if that was...
Do you have any idea how big, I mean, the pieces of DNA are that this... Because our adducts are just one DNA base. So they may be a little bit too small.
Okay.
Maybe.
Sure.
I've not thought about that.
Interesting to kind of discuss. But yeah, I mean, prostate cancer and the kind of etiology of this and the age at which most men get prostate cancer has always been kind of interesting to me, because you hear about, oh, it's all testosterone, but it's not like young men that have high levels of
exactly. It's when they're beginning that the estrogen is coming up and the testosterone is going down.
So it's kind of been an interesting thing to when you think about it. You're like, well, if testosterone was really wouldn't it be young men?
Yeah.
And so like you're saying, maybe it is. So the drop in T and maybe a proportional increase in estrogen from aromatization or whatever is priming the prostate to form these adducts with the testosterone. So along those lines, I mean. I know you're not a clinician per se, but a lot of people are taking hormone replacement therapy. Low T clinics are popping up all over the place. I'm sure in Omaha as well.
Oh yeah.
What do you think about men doing? I mean, is that playing with fire? Do you think?
I don't think it's on this particular subject. I wouldn't think. I mostly think, from what I understand, is it's all fairly pointless. That it really isn't doing what they all claim they're doing. It's not making that much difference. It's a pretty good scam, frankly. It seems to me there are other problems out of high testosterone levels that before you would get to the cancer problem.
Accumulating iron and hyperlipidemia and blood pressure.
And emotional problems and
Now, what about for women? I mean, women are going to these HRT clinics as well and getting on estrogen and progesterone.
Well, there's a lot less of that than there was, and I think the doses have all been lowered, which is a good thing. You know, there have been studies for HRT that have, I'm not going to say they've proven, but they've certainly shown evidence that the problem is not with the estrogen, but it's with the progestin. Because in the United States, everybody uses this synthetic progesterone, progestin, which they use because they can patent it. That's why they use it. In Europe, they're far more likely to actually use progesterone. And I've seen studies, there have been studies published that show if you use that, you don't see any effect. Right. If you use the synthetic progestin, then you end up with problems, with cancer, with breast cancer, actually. And so...
Which is a shame.
Yes.
So drug companies you can't patent a natural molecule, so they're creating a synthetic molecule, thinking it's so structurally similar, but it has all these downsides.
To be honest, I don't really follow too much of what women do, but my impression was that the advice these days, on the whole, is to only use HRT if you really have symptoms that are really unpleasant, and to do it as minimally as you can to see if you can get past the symptoms.
Yeah. So minimal effective dose.
Yeah.
Which was good advice. Yeah. I think we're never going to be 18 again, right? Hormonally.
Sure.
So
that's for sure. Yeah.
Yeah. Super fascinating. Now, there's a lot of nutritional compounds that you've talked about over the years. Resveratrol. We talked about this broccoli-derived sulforaphane,
n-acetylcystine.
Yeah, different compounds. How do you feel about those?
Well, I'm very enthusiastic about the combination of resveratrol and n-acetylcystine. I think that is pretty successful, and that's marketed. And I only have anecdotal information about it, but all of the anecdotal evidence, that I have are people saying that they see it seems to be they're not getting cancer. So that's good news. We've done a little with sulforaphane and decided it didn't seem to be so effective. I'm aware of some other groups that have done bigger studies, much bigger studies, and I make the guess that since I've not seen any of this published, it didn't go so well. That it didn't do in humans what they thought it was going to do. Let's put it that way. So,
you're not sold entirely on sulforaphane for that mechanism.
Right. Once again, we were able to do one small study with resveratrol and n-acetylcystine, and there's once again from funding problems. We can't get it funded, and so
it's tough.
But all we were able to show in that study was after 3 months. All we looked at in there was adduct levels, and they had gone down significantly in almost all. There was one woman in this study that they went up, and we have no idea why that happened. But in all the others, they either stayed the same or went down, and the overall difference was statistically significant of a decrease.
Wow. How many subjects were in that study?
Well, like 25.
Still, I mean, it's enough to get enough sample size to look at significance.
Right.
Going back to sulforaphane, in sulforaphane's defense, so it's really, when we talk about supplemental, it's glucoraphanin, right, that's converted by the enzyme myrosinase made in our gut bacteria, and there is different potencies and derivations of that. So what companies are doing now, to my knowledge, is making a double-layered capsule where you have the glucoraphanin in the inside, and on the outside you have the myrosinase, so that when you ingest it, it's being converted to sulforaphane. Okay. So yeah, there has been a lot of different, I know Mark Rydell, I believe at UCLA, is using just pure broccoli sprout extracts, which do have the myrosinase to activate the glucoraphanin. Okay. Anyway, so it's a unique biochemical. It's kind of like garlic and allicin.
Right. So far as I know, the studies that I was aware of that I suspect didn't work out very well, I think it was just a matter of sulforaphane, and perhaps more sophisticated approaches to it, like you're talking about, would make it more effective.
Sure. But resveratrol and NAC, I mean, those are pretty affordable. Resveratrol is more on the expensive side now, but NAC is
nothing,
super affordable. And do you recall the dosages? Are they on a gram a day or something like that? Or
well, the formulation that we're enthusiastic about is to take it twice a day, so it's always, there's some there, and it's works out to be about I think it's 250 milligrams of resveratrol and 200 milligrams of n-acetylcystine twice a day. Okay. So that's close to what you're talking about.
In that ballpark. And I recall that, is it Preventium? Is that?
Preventium is one,
Okay. So there's a few others.
There's
remember,
some others,
Sorry, it's been years since I first heard you speak in Colorado, friends. Just want to let you guys know. And it was 2008 you went out there for the functional forum.
I remember that, I remember. That was fun. I enjoyed that.
It's a good group. There's been so much. I think Colorado, and then the Denver, Boulder area, and Seattle and stuff is like a burgeoning hotbed for that sort of space.
It is. Yes, I was out. Actually, I was out in October for, I'm not even sure, I don't remember now what the name of it, but like a Dutch test meeting.
Cool.
And that was really interesting to me.
In Colorado or Seattle?
In Portland.
Okay. Carrie Jones, do you remember? Did you meet her?
Yes,
exactly.
Yeah,
she's been on our show before.
Yeah.
I remember seeing Instagram pictures of that conference. How was that?
Oh, it was fascinating.
Cool.
I thought it was really, really interesting. And it was, I have to say, it was a lot of fun for me to see speaker after speaker get up and the estrogen metabolism that we pioneered and talked about, it's just all part of their stuff. And it's not like there's anything earth-shaking about it. It's just there, and it's all part of their thinking. that's really very gratifying.
Right. You've influenced so many people.
Yeah.
Yeah, I think your work single-handedly caused people to rethink how estrogen is metabolized and the associated health risks. So that's awesome that you're here sharing the message and continuing to publish research, and that's amazing. So, gosh, you've been studying cancer, was it over 30 years now, rough? PAHs and then the
It's been a long time, yeah.
And now you're
like more over 40 years, to be honest.
Wow, that's amazing. What drives you for? Was it just serendipitous that it was cancer in the first place, or is there something specific?
No, I really wanted to. When I went through graduate school, I really wanted to then focus on cancer, and that was a choice for me. I wanted to do that. The first cancer lab I was in was a viral cancer lab. I was there for about a year, and I pretty quickly discovered that was not my area of expertise. I could do a lot better in chemical carcinogenesis. And so,
do you worry about our environment? We're talking offline about fracking and this. I mean, is there a lot of people kind of poo-poo, they hear about toxins and detoxes and they think it's snake oil, right? But there's a lot of novel compounds in our environment that affect biochemistry in a negative way from a cancer standpoint. And are you how worried are you about that?
I worry about it. I wouldn't say it was my top worry, but I think that the stuff in the environment, I think the changes in some of our basic food and I understand that, wanting to make plants easier to grow, more productive, more, higher yield, all that kind of stuff. A lot of that's admirable, but I suspect things have really changed.
Yeah.
The composition. I mean, I'm quite sure that, for example, a lot of wheat now has more carbohydrate and less protein and things like that.
Yeah. And potentially residual herbicides and pesticides.
Yes, that too.
More reports are coming out about that, which is kind of frightening.
Yeah.
Yeah. So we need good livers, good cytochrome P450 enzyme systems, and all that sort of stuff. So, Eleanor, what's next on the docket for you? You're working with a researcher at Harvard. You were saying about the cornea.
Right. We're involved in this study of this corneal. I don't know if disease is the right word, but we'll call it a disease called Fuchs eye dystrophy, where the corneal cells begin to get misshapen, and eventually you can go blind, and the only treatment for it is a corneal transplant. And what we found in collaboration with this group at Harvard Medical School is that these cells make a lot of estrogen DNA adducts, and we think that has to do with why they begin to misfunction, and the group has evidence that cytochrome P450 1B1 is involved, and also that working on to see whether n-acetylcystine could prevent this. And so that we're kind of in the middle of that. That's the most exciting thing that we're doing now.
At present. Now, why would the cornea tissue make higher prevalence for whatever reason of these catechol-estrogen quinones?
I have no idea.
It's crazy.
I don't know.
To think that estrogen is getting to the eye. I mean, it's funny to even think about.
Yes, it is. It really is. And no idea.
Because the prevalence of this particular cancer is much higher in women, which
this is not cancer. This is this is not cancer. It's a disease of some kind. I mean,
degenerative eye disorder.
Yeah, yes.
And it causes blindness, or
eventually the cells. Well, when the corneal cells they begin to get misshapen, and the cell wall breaks down, and you just don't have those cells that are doing whatever it is your corneal cells do. Yes, you can go blind. And
scary.
I never heard of it before. And then when I mentioned it one day, I discovered a friend is in early stages of this, and so I don't know that it's all that common since I never heard of it before, but it's significant, and so
Scary.
yeah, I know, scary. Like,
yeah, losing vision, losing eyesight.
That's just the worst.
frightening.
I was thinking, it doesn't have anything to do with macular degeneration, but that just sort of really scares me.
Oh, it absolutely does. There's some interesting scary animal models, not to change the conversation too much, but showing that LED light and screens induce neuroexcitotoxicity just by the wavelength of their light, at least in animal models. So my next kind of question was perhaps this increased prevalence of this eye disorder and estrogen metabolism could be in part maybe linked to screen time. I don't know.
Maybe.
The combination of hormone imbalances, screen time. That is frightening because now we see kids that are on devices, and a lot of people are just spending so much time on their phone. So anyway, fascinating stuff. So Eleanor, I'll put links to some of your papers in your lab here at University of Nebraska Health Sciences.
But or probably more correctly to say it's out online.
Oh, okay.
It'll have it's a DOI number.
Oh, yeah.
You know DOI numbers?
Yeah.
Okay, it's a DOI number.
Cool. So you can find out on PubMed if people want.
Oh yeah, yes, yeah.
I see. So that's kind of the how the academic process works. So it will be available, but it won't hit the journal actually.
The printed copy of the journal, yeah.
So
but
there's a lag.
if you go out to the journal and you kind of look at recent articles, you'll find it in there.
Cool.
And yeah, no, I'm really excited about that.
That's awesome.
Just to show this in another, because I think what I really think, without a lot of data for it, is that I think this whole formation of estrogen DNA adducts is actually a fundamental mechanism of, let's say, a mechanism of disease. And it's probably involved in a variety of things. I don't know what they are, but here's an example of something else besides cancer that it's involved in. And so I think it's a fundamental mechanism.
Right. So now we have decent evidence about prostate cancer, breast, ovarian, and potentially now this eye disorder.
Yes. We've also done a study in thyroid cancer. So, yeah.
Wow.
Yeah.
Any other besides?
No.
Okay.
We could leave it at that.
Yeah. Now, did the prostate cancer interest, did that kind of fizzle out? You said this one gentleman in the 90s, or has anyone kind of...
Oh, well, let's see. We published ours. We're back to the problem of money. We can't get it funded. Actually, the irony of the whole thing, I'll tell you this, that is, so in 2006, Jeff Bland invited me to come to the annual IFM symposium and give a lecture. And in fact, that year they gave me the Linus Pauling Award.
Wow, congratulations.
And, yeah, the plaque's up there on the wall.
Cool.
And it's one of them up there.
Yeah.
And so one of the guys there, one of the people there at this meeting was a physician from North Carolina who called me up and said, I've got these two guys that I think are highly estrogenized. Could you measure estrogen in their urine? And I said, sure. Even though we couldn't do that. I didn't know how to do that. And in fact, we had decided on the Adducts that we weren't going to look in urine because, we could just envision the lab with all these jugs of urine around or vast freezers where, it didn't sound like a very good idea to us for what we had done in animals. But at that point, with a collaborator who's at Kansas State, we had a monoclonal antibody to one of the DNA adducts, one of these depurinating adducts. And I said to myself, well, instead of measuring the estrogen, we'll measure that. Because I knew we could do that. Because he had set it up so you could take a sample and pass it through an affinity column that had this antibody on it. And the antibody would hold the adduct, and then you get rid of everything else, and then you use a different solution to wash the adducts out, and you have it in a little volume now, and it's clean, and you can put it on your instrument and analyze it. That was what we were planning to do. So, and what we did do. But, so, he said, well, I'm going to send you 3 samples. So he sends us these 3 samples of urine labeled A, B, and C. And meanwhile, I told my colleague in Kansas, and they apparently spent a week making their instrumentation as sensitive as they could possibly make it. And so we sent them, we got the urine samples here, we cleaned them up a little bit, and we sent them on, an aliquot on. Meanwhile, we analyzed them here ourselves. But, so I don't know, a little bit of time goes by, and my friend in Kansas calls me up and says, you have to break the code on this, the ABC, because one of the samples has so much of this adduct in it that we had to go back and put the instruments back to their regular calibration because it just, was way over the top. It was too sensitive. So, of course, it was the guy that had prostate cancer.
Wow.
And so then we got some more samples from a colleague at Hopkins from guys with prostate cancer, and we published the first little paper on this one adduct, not on all of them, just on this one. And in that, the guy in Kansas measured the adducts 2 different ways, and we measured it a third way by mass spectrometry, and you can see that they don't numerically coincide, but in all the traces, all the samples, they're similar between the 3 methods. And that was our first paper, and then we published another paper where we did measure all the adducts later. But so we said to ourselves, well, if we can measure this in urine from men, undoubtedly we can do it in urine from women. And then we started seriously looking at women, and we worked it all out in women with or without breast cancer. So
really?
So it was
it's
just
actually
kind of
the men that initiated
we
the urinary...
did the first, and then we came back to men later. But we got off on the women first because the women with and without breast cancer or at high risk for breast cancer were the best. It was the best place for us to go to try to get the most information we could get.
Wow. That's really fascinating.
Yeah.
Have you stayed in contact with this doctor in North Carolina? Or?
Oh, not recently. I suspect he's retired. And he was not actually an oncologist. I don't really know. I never quite understood why he had these patients, but he did. And so, no. But we ended up, the ovarian study, we ended up doing it at a colleague of his in North Carolina.
Wow.
And
that's great.
If you sit back and look, it's just all crazy because we did this. That study was funded by the Department of Defense Ovarian Cancer Research Program. And we did the study. We got these results that were just over the top about the polymorphisms. And the program officials were so excited about it that they included it in their report to Congress that year of what had come out of the program because they had to give a report every year to Congress. So we went back in to extend the research. They couldn't have cared less. They had absolutely no interest in funding that.
Gosh.
You just have to say, okay. That's the way it goes.
How do you deal with that on a personal level, that almost rejection, because you feel like you're so close to maybe just getting a few...
It's very frustrating. It's extremely frustrating. And
so do other researchers, do you guys have like a support group where you can talk? Because you're not the only one.
Not really. I think because I did most of this work with this longtime colleague who's now retired, we would probably never have survived if we hadn't had 2 of us with different skills that could, and could just support one another in various ways to persevere. Part of it, I think there's also an element of luck that you can make a discovery that doesn't inconvenience other people,
Yeah.
or that doesn't not more than inconvenience, doesn't threaten other people, because I mean, I'll give you what's probably the main problem for us, which is that in our view, this whole initiation of cancer by estrogens, it doesn't require the estrogen receptor. Now, I personally think the estrogen receptor is really important as these initiated cells, these cells that have mutated and are starting to be cancer cells, as those actually develop into a tumor you can detect. I think the receptor is very important there for all that cell division and growth, etc. But you don't need the estrogen receptor for the cancer process to start. You instead you have got the estrogen, damaging DNA. So that's not popular because the people who gained the most power in the whole estrogen field at the beginning were all receptor people, and it was really heretical to say that the estrogen receptor isn't so important. And that really creates a lot of problems. I mean, that's the big controversy here. I think some people could resolve this by saying, okay, well, I won't work on estrogen DNA damage anymore. I'll work on an estrogen receptor project that I can do, because that'll enable me to stay in business. I mean, I think a lot of people make those kinds of decisions.
They just pivot midstream and say, there's no funding in this.
Yeah. And I'll just work on something I can get funding for because I want to be a professor at a university and do research. That's the career I want. And I've never really been able to do that.
Good for you.
And then since the university decided to form a College of Public Health in 2007, and by a series of events I was asked to join it and asked to form this department, et cetera, I had other things that that sort of kept me in business while I was, even though the lab doesn't have all that much funding.
Okay, so that's how you kind of
Yeah.
straddle, so to speak, to make it all work,
Right.
which is really, really good. Now, just kind of final question here, I guess, on the estrogen receptor. Is it just because it's been talked about so much, or there's been so much interest there, or is it because there's drugs that can affect their estrogen receptor, as to the disparity in funding?
Well, I think the disparity of funding comes from most people thinking of the estrogen as a hormone and not thinking of it as a chemical. And also, I mean, the whole of chemical carcinogenesis, which may well have gotten a little crazy in how it was all handled, but it's disappeared. I mean, the National Cancer Institute doesn't do much about chemical carcinogenesis anymore. That whole branch went away. They decided it wasn't important.
When was that? Recently, or
10 years ago.
Oh.
I mean, we were
Could that
really
be
good.
that there's conflicts of interest or lawsuits, or because there's a lot of companies making chemicals, or it just...
No, I think they just... I think, I don't think anybody knows how to deal with the fact that there are thousands and thousands of new chemicals every year, and what could you ever do about it? I think that's a problem. I do think probably a lot of money was wasted on really expensive animal trials on compounds, all that. Well, I think, and I have to say this is kind of funny because it's kind of a role reversal for me and my longtime associate. I think chemical carcinogenesis really worked itself into, that whole field of study worked itself into a bad place out of the PAH, which are probably the most thoroughly studied carcinogens. There's also the nitrosamines, but that are really different. But because they worked themselves into insisting that this one metabolite was the carcinogen, and everything worked that way. And very few people, and they weren't willing to say, maybe this isn't as absolute as we're saying. And then they got to the place that they couldn't do anything with it because it wasn't working the way it should be working if that was really true. And actually, I think that what they thought was this important mechanism is probably a minor mechanism, and so then they had nowhere to go, so they had to go someplace else, And that, I think, is the reason why the whole field kind of fell apart.
That's crazy. So on a personal level, do you try to avoid charboiled meat or smoked meat at this point in your life? Or are you worried about the PAHs?
A little, yeah. I don't, yeah.
Not the worst, but not the best.
Yeah.
Kind of thing.
Yeah, I guess I worry more about the air pollution and the smoke and stuff. I mean, I'm glad even though they smell nice, we don't have too many wood-burning fire. I mean, you can't burn things in Omaha anymore, so you don't have much smoke in the air. And they're closing. The power district has a big coal-fired plant in North Omaha, and that's in the process of being shut down. And I think that's really good for the people that live there.
Yeah.
And
so the air pollution is probably a more pressing concern.
Yeah, I would think that. Yeah.
Yeah. I mean, it's interesting, just some of the data. People that run near major freeways and stuff accumulate more environmental toxins that are linked with mild cognitive impairment. And I remember I used to work in Chicago and like Lakeview Drive, I believe. All these people were running at rush hour and there's cars that stop. And I was like, oh, man. I mean, it's good that you're running, right? You don't want to deter exercise.
But that's probably not the place to do it, yeah.
Yeah. It's it's a popular, the world is just burgeoning.
Yeah.
So, Eleanor, again, want to commend you for all your work that you've been doing, and I'll put links here in the show notes. Probably close to one. You got a boogie.
Yes.
But yeah, if people are interested in learning about more what you do, should I link them to your website, or what would be a good resource?
You can link them to my website.
Okay, put that in the show notes and below. And thanks again for coming on and sharing your work.
Well, you're welcome.